Okay, everyone, thank you so much for joining today's session. Today we have Graham Stevens here with us. He's going to be discussing electronic design for real-world challenges. So we're so happy that all of you are here. If you're watching on YouTube, be sure to hit the subscribe button so that you get notified when we upload new videos. We hope that you're enjoying the KVA learning experience. Please be sure to check out our upcoming sessions. Next week, we're going to have a session on Autodesk Vault and how to fix mistakes using AI technology. At the end of this session, you can also fill out our survey. Give us some feedback. Let us know what topics you'd like to see covered, or if you're watching on YouTube, leave us a comment. Let us know what topics you'd like to see covered so that we can help better this program and make it better for you. And lastly, if you're not already partnered with us, be sure you can send us an email. You can check out our website at KETIV.com. I wanted to drop a link to an ebook here that you can also check out. Reach out to us. We're here to help you with topics that you'll see in today's presentation, as well as other topics for your manufacturing business. So be sure to check out that ebook, and I'll let Graham take it away. Thank you again for joining, everybody.
Yeah, thanks. So hi, I'm Graham Stevens, an application engineer focused on Ansys products, 25 years of product development, consulting, and simulation. And I provide application support for high frequency and low frequency electronic applications, as well as optics. And today we're talking about Earth environment electronics. Last month we did one on space in terms of all the different environmental conditions that you encounter in space and how do we design for that. And today we're going to be talking about Earth and what are all the different environmental conditions that your electronics might encounter here terrestrially, and then how Ansys can simulate and solve for those. So when we think about PCB reliability and how long these things last, this is kind of a fun slide where there was a red ring of death that Xbox ran into that cost actually $1.15 billion when the cost of repairs and lost sales were accounted for. So when we get to electronic reliability, and this was caused by a connector overheating and breaking, it can be really expensive for your products and have very high consequences. So what we're after today is showing you all the different ways to simulate this before you even prototype the part, so that you can avoid reliability issues like this. And it is typically very difficult to find information about PCB reliability that's valid in terms of, well, you know, what are all the typical failure modes and how important is this one versus that one? This is one picture of that from the US Air Force Avionics Integration Program, a little bit more focused on mechanical failures here, looking at thermal and vibration issues, in particular solder joint fatigue and cracking and thermal cycling being very important. You can also see humidity and dust here. In addition to these types of failures, there are, of course, electronic failures relative to the design electronically. And so in this next slide, I've sort of presented all the different types of environmental challenges that your electronics might encounter here on Earth relative to having a long lifetime electronic product. And then there are a number of Ansys solutions here indicated. And so today what we're doing is a survey of the different solutions that Ansys has relative to these different challenges, so that you're directed towards the right product and the right kind of workflow. So we're really focused here on workflow and how do we solve these and what do we do. And so, of course, for electronics, one of the primary failure modes has to do with temperature, where high temperatures reduce component lifetime. And when we think about modeling the thermal conditions of products, Ansys has a couple of different products, Ice Pack, Mechanical, and Fluent, that are useful in examining temperature and the impact on products. For vibration or dropping, Ansys has a mechanical suite that models those. On the electronic side, for signal integrity and power integrity, if you're looking at noise or distortion or losses of signals going from one place on your board to the next, or if you're looking at voltage fluctuations or hotspots, SI Wave is a tool that examines PCB boards for those issues. When it comes to humidity and moisture, you can use Fluent or Sherlock and Mechanical to look at humidity and moisture ingress. When it comes to EMI, EMC issues or lightning or transients, then another product called Charge Plus, as well as SI Wave and HFSS can help determine whether your shielding and designing and filtering is adequate. On the dust side, similar to humidity and moisture, Fluent and Ice Pack can play a role. If you're looking at electrostatic discharge or potential arcing, Charge Plus is used to model those problems. And then finally, when we're looking at trying to estimate reliability directly and get a mean time between failure, a product called Sherlock will help you do that as well. And so all of these different products and different workflows can help address all of these issues on the reliability side for your PCB and or total systems. And so, as I said before, we're really trying to simulate before we get to the design stage. So normally our typical business as usual design cycle is we design it, we build it, we test it. Did it work? If it did, then we're good to go. But if it didn't work, then we fix what breaks and keep going through this cycle. And so what we're trying to do is anticipate in the design stage where it's very easy to make changes before we get out to the field and we have field failures and we have to go make changes out in the field, which is very expensive. We want to design this in the computer, test it and simulate for faults in the computer before we even build it, then test it, hopefully have a very sharply reduced number of test fix cycles, and also have a sharply reduced number of field failures or recalls that you would need to deal with as well. And so what we're really focused on here is workflows that help you reduce those recalls or warranty costs in the field. And so just taking that list of different failure modes, and we're just going to kind of walk through them one by one. So the first one is temperature. And so when we're doing temperature simulations, typically we're trying to test for, is the current too high in operation or under some sort of high stress or abnormal operation condition? Is my cooling inadequate? Typically you would have a heat sink and cool your electronics. And we want to test and see if our cooling scheme works. And then there may also be some multi-physics simulations that might be useful in this situation where you have thermal mechanical stress arises, or you have your temperature regime is so high that the conductivity of copper changes, which then changes Joule heating, which then changes your stress, your thermal stress, and you might need a two-way coupled analysis. So these are just some of the different types of simulations you might run in terms of testing whether your design is going to work thermally. And as we're looking at this, we're also typically designing some sort of failure protection scheme. So is my heat sink working? Does my fan work? If I'm shielding from radiation, does my shielding work? And your typical solutions here are kind of listed here in terms of these are some common ways that engineers use to design around heat and manage the heat. So you might have heat sinks, heat pipes, heat spreaders, thermal interface materials. You might have different cooling schemes, whether that's air cooled, liquid cooled, or a thermal electric cooler, different types of shielding, enclosing, or insulations. Have different types of components. Some components might be ceramic based as opposed to plastic and therefore more resistant to temperature. You might have higher thermal conductivity materials or lower thermal conductivities in your design. And finally, you might have active designs or passive designs where you might have sensors integrating and manage the thermal conditions actively. So all these different protection schemes we have to simulate and try and figure out, is it working? How do I design those systems? What's gonna work? And so in the Ansys universe, there are 3 different thermal packages that do this kind of thermal modeling. Typically for the electronics area, we focus on AEDT IcePack because IcePack is a package that's been sort of special purpose design for electronic box cooling. So there are fans and heat sinks that are sort of automatically created, or that you can sort of drop in the design, sort of a drop and go design philosophy. But we also might be looking at, mechanical stress. And so then there's something called AEDT mechanical, or even Ansys mechanical, if you're starting to look at some of those. And then, of course, we have Fluent, which is the CFD flagship solver for the Ansys universe that's used for really, complex and difficult fluid problems. So between IcePack and Fluent, typically where IcePack can't handle it is if you have some sort of a multi-phase flow, then you would need to go to Fluent, but for the most part, you would stay with IcePack. You might also have different familiarity with these different interfaces. So AEDT is a different interface from Ansys Mechanical, is a different interface from Ansys Fluent. Typically, you want to sort of lean on or go with the interface you're most familiar with. And then, of course, in mechanical, you might have some limitations relative to some sort of a steady state approximation or a heat transfer coefficient surface approximation that you might need to make in mechanical. If you can make that, please use mechanical. It can be faster sometimes than IcePack as well. But if not, then jump to IcePack to handle those changing conditions, heat flows, and full 3D spatial variations. So this is just a brief overview of which thermal package you might want to use. And then when we think about thermal reliability, we also have to start considering scale. So IcePack can be used on all these different scales at the chip, the IC package, board assembly, back plane assembly, system level, and some sort of open environment level. As you go to higher levels of abstraction, you may want to go to some sort of a reduced order model or some sort of a thermal network to make the calculations more tractable. But Ansys can handle all of these different scales. And as we're doing these different scales, we also have different packages that interface. So we can interface with structural or reliability or electromagnetics. If we're looking at joule heating and trying to estimate the amount of heat in the design, we might go to an electromagnetics package to determine what those thermal sources are, feed that into our thermal simulation, and feed it back to the electromagnetic package in a two-way simulation. If we're at the PCB level, we might want to use SI wave, and if we're at the chip level, we might want to use Red Hawk. So this is sort of how these thermal simulations are integrated with the rest of the Ansys universe. So there's a lot more detail here relative to IcePack. I did want to emphasize just a couple of slides relative to electronics. On the PCB side, one issue that is really problematic relative to simulating PCBs thermally or otherwise is that there's a tremendous amount of detail in each of these PCB boards, very fine detail. And if you do that in a finite element analysis, you might have way too many elements that makes it much more intractable. And so IcePack and Mechanical has something that allows you to, it's called trace mapping, we'll get to it in a minute, that allows you to make those simulations more tractable, where we chop up the board into a grid and then calculate the conductivity of all the elements that are there and then feed that into the simulation. But these are just some examples here of what IcePack can do in terms of looking at your temperature distributions, your electric potential distributions, etc. So as I mentioned, IcePack is a solver for electronics thermal management. It's typically sort of special purpose designed for this. I've got a package with boards, and I'm now trying to cool it, and I'm wanting to simulate both the airflow through this package as well as the conduction and or radiation. And so it can handle all of those. It uses the fluid CFD method and solver, but without quite as many bells and whistles in terms of the underlying mechanics of solving, to make it a little easier for electronics folks to just sort of jump in. And these are some examples of these kinds of IcePack simulations where we're looking at airflow or conductivity, temperature contours, particle traces, so generally sort of velocity of air or temperature impacts. So now switching gears to the next row in my previous table onto mechanical side. When it comes to mechanical reliability, as I said, Ansys has a mechanical package that can model all of these different situations, whether it's the trace mapping and reinforcements, but solder, coatings, potting, underfill, drop tests, and look at shock and drop events, look at moisture ingression, etc. So all of these different kinds of tests you would want to, or simulations you would do in mechanical. And there are, just like in the thermal side, there are a number of mechanical packages in the Ansys universe. We have Ansys Mechanical itself, which is sort of the flagship mechanical package. There's AEDT Mechanical, which Ansys put some mechanical capability into the Ansys Electronics desktop for convenience for electronics engineers. And then, of course, there's LS-DYNA. So this is just a brief chart around the different kinds of mechanical models you might need, and the different levels of different license levels that you might need in Ansys Mechanical. In general, AEDT Mechanical is sort of looking at steady state transient, relatively simple models. If you need something more complex, you'll need to jump to Ansys Mechanical and go back and forth. And then finally, if you're doing a drop test, there you can do that in both Ansys Mechanical or in LS-DYNA. But do please reach out to support@ketiv.com when you're looking at decisions relative to which level do I need and what am I trying to do in terms of physics. And we're here to help in terms of helping you figure out that. And as I mentioned, the trace mapping capability also is in mechanical here. And this allows us to really get a better sense of what's going on, both thermally, but also for warpage and vibration simulation results as well. And this is just a brief outline of how do I tell if I need LS-DYNA or not. So typically you would use implicit methods, which is Ansys Mechanical, for your sort of problems where you're looking at something greater than a second. So steady state for sure, but then you might have some sort of static or dynamic situation or quasi-static situation. But if you're getting into very high velocities or very fast phenomenon that are less than a second, it may be more computationally efficient to use explicit methods in LS-DYNA. And then lastly, I wanted to refer you to Improving Mechanical Reliability for Electronics, which is another webinar similar to this one that surveys more specifically on the mechanical side, mechanical workflows. So please see that for future mechanical workflow, further mechanical workflow information. As we're sort of doing a broad brush now and just want to, can't quite get to every level of detail. So jumping again now to the third row on my previous table in terms of conditions we might find, we're looking at signal integrity. And signal integrity is when you're examining your signals that are going from one part of the board to the other. They might be digital here. It's a stream of bits, ones and zeros. They might be analog, but we're interested in the integrity of the signal. Is that signal being interfered with? Is it merging? Is it getting transmitted appropriately. And that is called signal integrity. And your typical analysis tests a design by throwing a stream of 1s and 0 bits at it, and then determining what comes out at the other end. And that's represented in an eye diagram here in terms of how well the signal was passed. And when we think about the design causes of signal degradation, it can be attenuation due to dielectric and conductor materials, reflections due to transitions or impedance mismatch, and you might have crosstalk or EMI due to other nearby signal conductors. So we can sort of see here for the PCB only, we have a really nice signal, but then with the PCB with harness, all of a sudden you have a huge amount of interference due to a nearby signal conductor. So this signal integrity is all about redesigning signal paths, double checking shielding, etc. And the tool that Ansys uses for diagnosing and fixing these issues before you even build the board is called SI Wave. And it's a specialized tool focused on PCB boards, looking at signal integrity, power integrity, crosstalk, and EMI analyses, and can handle your high-speed devices. And so SI Wave has all these different capabilities, looking at crosstalk, am I getting interference of one signal to the other, looking at characteristic impedance, time domain reflectometry, DC analysis, AC frequency, decoupling capacitor optimization, and finally an EMI scanner. All these different capabilities are sort of focused and special purpose built for these purposes, doing signal integrity. So some examples is I might have a serial deserializer design. I've got typically a wire that's going into my board. We might use HFSS to actually look at the transitions in the routing, but then once we come to the board level, we use SI Wave to validate the entire signal at root and make sure the signal is getting where it needs to go. And a new capability that's arisen over the last few years is the ability to do flex PCBs as well. And so if we look at different positions that the flex is in, and then how does that impact the signal, this is a new and exciting capability that Ansys can handle. And then if we look at power integrity, it's somewhat similar to signal integrity, but now we're looking at voltage ripple and minimizing that. Or looking at current to see if we're getting hotspots. And so we can use the same tools where we've got many inductive loops, capacitive planes, and resistance paths. We have to account for all of that. So we really do need some sort of a field solver such as SI Wave or HFSS to handle these, especially at high frequency. And a typical SI Wave power integrity workflow looks like this, where you import your ECAD design, do your component mapping, set up an SYZ simulation to look at impedance for the power delivery network. You can sort of see here's a bare PCB, and with capacitors, you say we're doing design to improve the impedance there. Look at your resonant modes. And then there's something called a PI advisor to help you with optimizing capacitor strategy based on your desired impedance mask. So all of these are different power integrity analyses you can do in SI Wave. In addition, on the DC IR side, you want to minimize the resistance of your power delivery network and validate whether you're getting shorts or you have enough vias. And so we do analysis, a DC IR analysis in SI Wave on the board to validate these issues. And then this is just, again, a sort of another couple of graphs showing sort of typical SI Wave analyses where we're looking at DC IR voltage drop on a PCB package, on an electronic board. Identifying excessive current, looking at current plot or eye diagrams. So moving along in terms of moisture ingress or hydroscopic effects, typically these are modeled in Ansys Mechanical. So this is one particular situation where moisture can be absorbed during storage and then mounted and then trapped inside a component, and you get hygroscopic stresses. This can be modeled directly, and we have a number of capabilities on how to do these kinds of models. Fluent can also play a role if you're really looking for tracking moisture or fluid flow through the design as well. And then on the EMI, EMC side, where we're looking at electromagnetic interference, both emissions, and is my device emitting too much radiation so that it won't pass standards, or is it getting affected by emissions? So are other devices or antennas out there, and are they going to interfere with the operation of my device? So these are two areas that Ansys focuses on. Typically, this radiated emissions simulation is also an expensive test, and we can now fully simulate your full device, both at the board level with SI Wave, using EMC Plus on the cable side, and then HFSS on the emission side. And then SI Wave's EMI scanner assists with EMI prevention in terms of design of the boards. So your typical process for EMC development for consumer electronics is you design the device, you do some EMC simulation and then mitigation, finally do some prototype fabrication and compliance testing and device production. But once you've reached this compliance testing stage, that is a very expensive proposition. And so you really want to simulate that before you even get there, and resolve those issues before you even get there, resolve them in the design stage where things are in flux, before you even fabricate the prototype. So Ansys can now simulate all of these and allow that. So as I mentioned, these laboratory EMC tests are expensive. They can only be performed by a physical prototype generally, and it can cost $100,000 to do a test, $50,000 to do a test in this anechoic chamber, and it's very expensive. So it's very useful to simulate this before you even get there and address issues, so that you just have to go through this once and you're done. One thing we've noticed with EMC simulations is that cables and enclosures are a very important part of this picture. So we have existing tools for printed circuit board emissions. HFSS can do that, as well as in particular SI Wave. But you really need to consider the cables. You really need to consider the enclosures and how the seams and the joints are done at the lids and tapes, etc. And so all that's relatively time consuming, and EMC Plus can help you solve those challenges and do these simulations. So EMC Plus was originally focused on cable modeling, in particular for airplanes and cars, and it allows you to address all of these different conditions. Most of this is a little bit focused on aircraft, but the same thing occurs in consumer products. So you might have lightning, you might have a lightning fuel tank ignition prevention situation, or aircraft level EMC to deal with. But in general, this technology has now been applied to consumer products as well. And so, as I said, we can simulate lightning events, both lightning strikes where they might occur and or what the distribution in the aircraft might be. We can look at cable to cable crosstalk, whether it's shielded or unshielded in various situations there. Its EMC Plus is also can be integrated with HFSS to handle where EMC Plus handles the cables and HFSS does the PCB board. And this allows us to get emissions results, both near field from the board or radiated emissions for the entire package. And sort of see the simulation here. This also is useful for low frequency products. So if I have a pump or a motor and I want to look at my EMI, EMC before I'm again, have to test that for certification purposes. We can handle that in terms of our CISPR 25 test. On the automotive side, when we're looking at the full electronics of the system, we may want to look at EMI, EMC to make sure the internal parts of my system are not affected by external fields and conditions, and or doesn't have too many emissions to users. And similarly, for whole powertrains, we can handle this. So we have, when we start looking at the system level, we bring in Twin Builder and merge it into all these different systems, and we can start analyzing everything. And then this is just one last slide looking at antennas in particular in terms of RFI interference, looking at the cables in particular and HFSS on the antenna side, but then we can do the SI wave analysis for the PCB board, and then also platform level analysis. If I have multiple antennas, how do those impact each other? How do those both transmit and receive with each other? And with another special package called emit that helps with that. That's EMI, EMC. And then for dust, similar to moisture, we can model dust directly, as shown in this cyclone filter example, in either Ansys Fluent or Ansys Rocky, or we can just look at seal integrity, typically mechanical. Please do contact support@ketiv.com if you have any questions about other analyses needed here, or how to run these or what packages. And then we come to electrostatic discharge and or dielectric strength or arcing, which can happen in our design. So Ansys Charge Plus is a product that specifically models arcing, electrostatic discharge, flashover, dielectric breakdown, discharging for patch antennas as well, and allows us to model these situations and make sure they're not going to impact our design, or that we've designed these kinds of situations out of the product. So typically for arc breakdown, we're looking at solving this Paschen equation in terms of electronic breakdown. Each of the finite elements, this is calculated, and then we can calculate arcs and model those. And we can look at them in a PCB board here, just looking at ESD coupling to the PCB from the enclosure. We can look at PCB flashover and arcing currents as shown here, and get a good sense of what's going on here in terms of arcing before we even get there. In addition, you can model your dielectrics in your design and make sure they also will survive the possible high voltage situations that you may or may not have in your designs. And then finally, there's Ansys Sherlock for reliability, where we take all the information from those other previous tests or simulations and put them into a package that can calculate the mean time between failure for each different component. So Sherlock starts with a database, a component database that allows you to get a pretty good initial picture of what your reliability is. But then you can marry it with HFSS, SI wave, ice pack, mechanical simulations with regards to powered signal integrity, temperature, or shock and vibration analysis, and dialing the accuracy for that reliability estimate to very high levels, and estimate the reliability of your PCB or your system as a whole. And so that's where Sherlock is used. So Sherlock, as I mentioned, allows you to estimate mean time between failure for each individual component. So you can identify which components might be at risk or an issue, and then focus on those and do more design in that area to reduce your risk. It also compares, it's got roughly 15 different types of analyses, all of them sort of listed here, that with the database that it has, you can run all of these relatively quickly. And then again, get a sense of where the design needs focus on the reliability side, what do I need to fix or improve, and ensure good reliability for your products as you move forward. And this, of course, takes into account solder fatigue, thermal derating, conductive anodic filament analysis, heat sink modeling, etc. So all the different things that directly affect reliability are accounted for in this tool and database. And with that, I will open up for questions. Wondering if anybody has any questions. Okay. So in conclusion, I just want to mention that Ansys can solve your real-world design, operating condition, and reliability challenges for electronic systems. Whether that's the really small ones up to the really big ones. And for additional support and resources, there's a number of different sources. Please do reach out to support@ketiv.com. We're here to help you with these designs and get going using Ansys software. There's something called the Ansys Learning Hub that is a repository of courses that walk you through examples and introduce you to learning how to use the software. These are the different learning rooms that are useful to learn these different packages that I mentioned here. In addition, there's an Ansys how-to YouTube channel for videos. If there's a particular task you're looking for, this might be useful. There's another resource here called the Resource Center that's a repository of webinars. And then finally, in innovation space are more free courses that are more courses at a more general level as opposed to package specific. So with that, I just wanted to mention that KETIV does simulation services in all these different areas, mechanical, fluids, and electronics. So if you're looking for some help and can't do it yourself or don't have the capacity, please do reach out to us for services as well. But we also are focused on getting you up to speed as fast as possible as well. So, but we do it ourselves as well. And with that, I am finished.
Thank you so much, Graham, and thank you everyone for joining. We'll see you all at next week's session.